So I've got a Sanyo Denki wire saving motor. It's got an incremental encoder on it, but it's wire saving, so the halls are transmitted in the encoder. I'll show you that, but first I want to show you how to connect the motor case frame to earth. So you can hear that the motor case, when you bolt it onto the frame, has a path to earth. And when you plug this into the drive, then the motor case has a path to earth because the drive is connected to earth. So bolting to the frame, good path to earth. Another method for getting earth, maybe there's a shield in here, but another path. But see, how is it possible that the motor case is connected to the drive earth if the motor feedback's not connected? That should be not possible. But you can see this encoder case is actually connected to the motor case. And there's a shield in here, which somehow they've connected it to the encoder case, which is connected to the motor case. So you got to make sure there's a good path to earth for the motor case so the PWM noise does not get into the feedback shield. And you got to make sure that pin 1, or the connector, the shield on this cable here finds a good path to earth, okay, through the connector. I would say disconnect the feedback shield from the encoder case, but some people do that, and maybe it's okay unless you have a problem, and then it's not okay. So let's take a look at the encoder. It's got an AA knot and a BB knot, which is the differential incremental, and this C knot is the index. And it also says U, V, and W. So the halls are actually embedded into this these wires. So brown, blue, brown, green, purple, white, yellow, with respect to red +5 and ground on black. And you can see that the shield they're showing that they're connecting it to the case of the feedback, but what they don't show is that it's actually connected to the case of the motor. So that's a bad idea. But they don't make this motor anymore, so or maybe they still make it, but maybe you should buy the absolute 2-wire with respect to a 4-wire feedback. There's a serial incremental too, I think, and a absolute encoder. Anyways, I'm going to show you the drawing here. I just put a big fat X there because I think that's a bad idea. Usually the motor company will just go out of business, but these guys haven't. So maybe the motor case has a good path to earth. You can see this motor, I'm showing a good path to earth when you bolt it to the frame, but there's another little wire that travels a long distance to get to earth. Some noise will come down this, but it's a PWM amplifier, so there's PWM to the coil to the motor case, the Miller capacitance. So just probably not a good idea to connect it to your encoder case, and probably not a good idea to connect your feedback shield to the motor case, because all the noise that goes to the case, if it doesn't find a good path to earth, finds a good path through your feedback device and can corrupt your signals. On Copley, we call it AA knot, BB knot, and XX knot for the index. And then again, these will be the hall codes on power up or reset. We should be able to see the code. So I'm going to show, so this was the model number for the motor I had, R2AA motor. There's an S in the part number, which is S for Wiresaving Incremental, and I guess it's on these other PP part numbers. Anyways, there's some other numbers here. The M would be with a CE mark, and the BL is a special code. Who knows, right? And then I don't see an A, planetary gear. Anyway, so that's the basic specification for the motor, and then of course the wiring guide. It's not intending to show the feedback the shield connected to the motor case because they're separated physically, but one could assume that if the feedback had a case, it would be connected to the motor case, and then the case should find a good path to earth. So I put that in the drawing. Let's take a look at CME. I'm using CME 8.1, beta 24. I got a BEL, so 09030, just an AccelNet panel drive, plus drive that works with absolute encoders or serial incremental encoders from the Japanese style or the Wiresaving. I got a firmware 4.36, which is from production. I think it works all the way down to 3.18, and then other firmwares I've tested, and it works just fine. So let me show you in the basic setup how we're going to set this up. Brushless rotary, maybe there's break, maybe there's not. When you pick, it's not just an incremental encoder, okay, because there's no halls. But you could do this, but you're doing wake and wiggle. What we provide is Sanyo Denki Wiresaving with halls on it. So that's on the motor. It's the primary feedback, and you can even emulate out the incremental. And there's a loss detection and index, because that's important too. You got to make sure there's good wiring for AA not, BB not, and XX not. And it's 8,000 counts per rev. Don't ignore your feedback if there was a break, blah, blah, blah. Take a quick peek at the motor. It's a 10-pole motor that talks to the electrical cycles. It's got some inductance and resistance and some continuous torque, and then some current to come up with Newton meters per amp, which folds back to the same thing as volts per radians per second. And then peak torque, usually 2 or 3 times the continuous, and some inertia. This one's a 0.27 kilograms centimeter squared. And some theoretical top speed, which on this one is 37 volts per kRPM. So you could go like, well, with 370 volts, you go 10,000 RPM. Maybe that's not a good idea, limited at 6,000. But I'm running off of 48 volts here, so I just put a rated speed in there. This should be more than the rated. And I calculated initial tuning values. I tuned the current loop. You see that's amps peak, not amps RMS, so a little bit higher than the label, which says A for amps RMS on it. And make sure your velocity limit is set high enough. This number must be greater than anything you want to do. You see the VP and VI have been tuned for this motor. And position loop, following error at 8,000 counts, a single rev, and some tracking. You could dial these down. Trajectory limits, abort jerk to 0. I'm going to set the, oh no, the jerk's fine. So the abort decel and the decel are the same. You might want to abort faster than your normal accel and decel. But these are just trajectory limits. Homing could be to an index. That's fine. Or to a limit, then back to an index. But the phasing is done on the manual phasing screen. You can see I can enable the drive and press and hold forward. Oh, I need more current. Let's give it the full 3 amps here. Oh, you know what? I need to hook up the motor power wires. Okay, so I had unplugged those. So I disabled the drive. Now I can enable the drive, deliver 3 amps. Rotate the current vector. See the Hall? The Halls come in on power up or reset, and then they're like simulated on the encoder thereafter. So there's not real Hall effect sensors except for on power up or reset. And this is a little bit of a lead. That's a little bit of a lag. No, minus 30. No, maybe 60. It's a little subjective here. There's a little bit of a lead and a little bit of a lead. So this is pretty balanced. I just did a Hall offset of 60 degrees. It's important when you go forward that your counts go up. You see how the counts go up. And you can see your current U, V, and W as it's rotating through the motor wires. You have 10 poles or 5 electrical cycles, north pole and south pole. Those are poles. And a cycle would be north to south. So you have to rotate this 5 times to see 1 rev of the motor. So let's go back here for a second. Set to 0. I got 0 counts. I go forward. And we can go a little bit faster. It's just going to be hard to land on 0. But 360. 1, 2, 3, 4, 5, 6, 7, 8. Oops. Okay, yeah, 5. 5 electrical cycles times 2 poles is 10 pole. Okay, and it's plus or minus a little bit for the accuracy of open loop microstepping, so it's kind of hard to land right on 0. But you get the idea. That's probably 8,000 counts per rev, and it's probably a 10-pole motor, so you can confirm that. If you don't like this clockwise to be forward, you could invert the motor, but when you do that, now the counts go down, okay, and so you got to invert the feedback, and then now your phasing goes the wrong way, so you got to change the motor wires to make them go the same way. Okay, and then I got like 180 degrees of, let's go slow again, 90 degrees. That's pretty good. I'd say it looks leading in both directions balanced, so phasing's okay. I just changed the direction of the motor. I didn't like going, I didn't like down to be forward, so I made up forward. So, and then once you do all the tuning, you should be able to jog the motor. Yeah, there we go. So just a nice slow jog on the motor, 60 RPM. Yeah, let's take a look at that. So I made counterclockwise forward, and then to change the direction, we have to redo the phasing. But you can monitor actual position, following error. So, I mean, plus or minus a count while we're moving, that's pretty good. Let's take a look at some tuning real quick. So, current loop. Auto press stop, auto setup checkbox, press start. Okay, so this is a good current loop tuning. If the CP was too high, you get a little ring, cut it in half. And then if the integral was too high, you get some integral wind up, cut it in half. And then the same thing for the velocity loop. I set some velocity parameters. Heck, let's do 250 here. See if we can still get a trapezoidal waveform. Auto setup checkbox, CH3 current, actual current. And so for these gains, yeah, if this is doubled, you got to start seeing a little oscillation on your current loop. Yeah, close to oscillation, knock that in half. Too much integral. You see this more when you're doing the position loop. I moved the pole on this guy because I have no load, so I just made it a single pole 300 hertz. Single pole 300 hertz, press apply, and maybe that gave me a little bit more bandwidth on this. But and then of course for position, this is going to be 10 rev move, auto setup checkbox, put in position, following error, okay, hit start. That's a 1 electrical cycle. 8,000 would be 1 rev, and 80,000 will be 10 revs. And you can see the current. I want current actual current. That's what I want. So for acceleration, you can see a little bit of following error, and there's your current. It goes up to an amp. I could have 10 times the inertia and hit 10 amps for acceleration. So before the move, 0 error. During the move, plus or minus a few counts. After the move, settle. Bam, you're at plus or minus 1 count within like 20 milliseconds. So as you can save this to a file, Sanyo Denki Wire saving file, and then you can save a file, CCX file, and load it. Checking the firmware, no faults, that's good. Checking the firmware, 4.36, that's the latest production firmware as of whatever, last few years, next few years.